For my ME445 extra credit assignment, since I'm doing it alone, I decided to elaborate on Lagrangian dynamics. In class, we use Lagrange to determine the dynamics of a rigid body with examples like point masses and 2R open chains, with the ultimate goal of finding the generalized forces, which in our case were the torques applied at our robot's joints. For some background, Lagrangian mathematics, its derivation pretty much mirrors Newton's second law of motion, which we all know is F equals ma. It characterizes the physical state of a system, and physically, it's the system's kinetic energy minus the system's potential energy with reference to each generalized coordinate. So you'll have one equation of motion per generalized coordinate. And like I just said, it computes the system's equations of motion by the following equation of partial derivatives, where lowercase f in this case equals capital F in Newton's second law, and that kind of shows how the equations both accomplish finding out the forces applied on the system. Next, I wanted to research a little bit about the Lagrangian, and I learned how it is related to the stationary action principle. Out of every possible path through space and time, an object will always take the path in which action is stationary. Action, in short, is just the label given to describe a particular path. The Lagrangian can be taken at every instantaneous point along a path, given that the kinetic energy and/or potential energy may be different at each point. What this really means is that you can't assume that the kinetic and potential energy will be the same throughout an entire object's path. Therefore, the kinetic and potential energies are enough to describe the entire trajectory. Therefore, the action can be computed by integrating the Lagrangian over time. If the variance, which is that integral, in action is 0, then we know that it is stationary action. In other words, which is more applicable to us, if the Euler-Lagrange equations shown on the previous slide equals 0, then the principle of stationary action will apply. The key here to using the principle of stationary action gives us a useful explanation of why objects take certain kinds of trajectories, or in the case that I'm about to explain, how we could determine the best trajectories for certain objects like autonomous vehicles. So in this real-life application, I went on to research more about autonomous cars, which are also known as connected automated vehicles, or CAVs. In simple terms, how do they work? Well, they rely on sensors, actuators, complex algorithms, machine learning systems, and powerful processors to execute software. The cars create and constantly add to a map of their surroundings based on sensors placed strategically throughout the vehicle. Some of these sensors include radar sensors, which monitor position of nearby vehicles, video cameras, which detect traffic lights, road signs, track other vehicles, and look for pedestrians, and also LiDAR sensors, which are light detection and ranging sensors, which measure distances, detect road edges, and identify lane markings. Then, using a sophisticated software process with all this sensory input, the autonomous car can plot a path and send signals to its actuators. And these actuators are in charge of accelerating, braking, and steering. So obviously, we can see the direct correlation between processing all of the sensory input directly into moving the vehicle. Although fully autonomous vehicles are not a reality just yet, companies like Audi, Infiniti, Mercedes-Benz, Ford, Tesla, and BMW, amongst others, have begun implementing many of these features into their newer vehicles. And research shows by 2050, autonomous cars hope to reduce traffic congestion due to ride sharing, cut transportation costs by 40%, free up parking lots for other uses like for schools or for recreational centers and other things of the sort, improve walkability and livability, and what I think most importantly, reduce urban CO2 emissions by 80% worldwide. So obviously, since not all vehicles are autonomous and we have a combination of human-driven vehicles as well as automated vehicles, we have heterogeneous traffic. Historically, this concept of traffic was analyzed using the Eulerian framework, but now, given its heterogeneous concept, we use the Lagrangian framework. And below is an image of the two compared to one another that I will explain further in a moment. For centuries, the Eulerian framework was used to analyze traffic patterns by observing traffic at fixed locations via loop detectors and predetermined locations on the road. Given the rise of technology and the increase in autonomous vehicles on the road, The Lagrangian model is based on data collected by individual vehicles, so it's more up to date. Eulerian framework ignores the time delays corresponding to both reaction time of human drivers as well as time delays in the control loops of these calves. So basically, in short, the Eulerian framework disregards any change in time, which is a pretty integral part to this concept. The image below shows a proposed figure of the Lagrangian framework in action. Each vehicle is given a number with respect to n, where n equals 0 is the lead vehicle. All elements are a function of n and time t. The most important variable is x of n of t, which represents the vehicle's position. The GPS system associated with each vehicle measures this function, x of n of t, and therefore we know that the function increases with time and decreases with n as the vehicles move opposite their numbering notation. So as you can see in the picture, the vehicles behind the lead vehicle are higher numbered than the vehicles on the right side. Something else to note is that a large assumption to this framework is that vehicles do not pass one another and remain in their assigned order. Using Lagrange to study heterogeneous traffic in the midst of a technological shift to the future of autonomous transportation is key to understanding the paths of each vehicle by their kinetic and potential energies relative to those of other vehicles, aligning with the core principles of Lagrangian dynamics we learned in ME445. I thought it was just extremely interesting, both mathematically as well as conceptually, about Lagrange. So being able to relate that to a very relevant real world topic was very interesting to me. That not only does Lagrange connect with, trajectories and path following, like I mentioned, but also later on with PID, it doesn't just apply to a smaller scale, robots and robot arms that we studied in class, but on a much larger scale with autonomous vehicles in the real world.